Hey everyone, welcome to BCP Med. In this video, we're going to be taking a look at the effect of resonance on the acidity of a given molecule. We're going to look at things like how resonance impacts the stability of conjugate anions and home in on specific examples of some substituted phenols. We're also going to look at some nitrogen and carbon acids and close with some complex examples of how resonance and inductive effects work together to give the acidity of some structurally interesting molecules. Let's go ahead and get started. Before we move forward in our discussion, it's very important to understand that anion stability is one of the main determinants of the acidity of a given molecule. The more stable the conjugate anion that is formed, the more acidic that molecule will be, the more the equilibrium of acidity will push towards the right-hand side. Specifically, being able to delocalize excess electron density associated with an anion or associated with that negative formal charge into other atoms or into other pi bonds will make the anion more stable. So that anion is somehow able to push its excess electron density into other atoms through a pi bond system. That conjugate anion will be more stable and the original molecule will be more acidic. And that is why resonance structures, or having more resonance structures rather, will allow an anion to be more stable and a molecule to be more acidic. We can see that if we look at the ethanol molecule to start, or rather the ethoxide conjugate anion. Ethanol has a pKa of about 16, which means it's just a little bit less acidic than water. However, if we go ahead and compare that to phenol, which has also an O- anion, we see that phenol has a pKa of about 10, which is 1,000,000 times more acidic than ethanol. So why is the phenol molecule more acidic, or in other words, why is the phenoxide anion more stable than the ethoxide anion? Well, in ethanol, or the ethoxide anion, the negative charge is just localized on that oxygen, which carries the charge decently well. O is relatively electronegative. However, it's just stuck there, it's confined to one atom. Whereas if we look at phenol, we see this structure has the negative charge localized onto the oxygen, but there's actually several structures which can be used to describe the phenol molecule. There are several resonance structures of how the negative charge can be distributed. This is because the anion is connected or adjacent to a pi system. And so this negative charge here can push to form a double bond on the oxygen, and then this double bond can go ahead and kick up to this carbon, and now the negative charge is on that carbon. It can also push in this direction to give us the negative charge here, or push like this to give the negative charge here. In other words, the negative charge on the phenoxide anion is delocalized between one oxygen, shown here in blue, and 3 carbons. All 3 of these are going to carry a partial negative charge associated with this anion, making it far more stable and therefore phenol much more acidic. It is even better, or rather, the molecule will be more acidic if you can delocalize into an electronegative element like O or N. Carbon is not particularly good at carrying a negative charge, so it doesn't matter as much. Right? But those O's and N's, being more electronegative, carry a negative charge much better. A great example of this is acetic acid, or the acetic acid anion, the carboxylate anion. Carboxylate can be described by either of these 2 resonance structures. In this case, though, the negative formal charge on this oxygen can go ahead and move onto this oxygen. And these 2 structures are equivalent. The oxygens share the negative charge equally. And so because you can distribute the negative charge between these 2 very electronegative oxygens, the anion is very stable. And so the original molecule is quite acidic. Acetic acid is a very strong organic acid, having a pKa of 4.7, which is 1,000,000 times more acidic than phenol, which is in turn 1,000,000 times more acidic than ethanol. So you can see how the resonance delocalization makes a huge deal here. However, it's important to understand that in order for the pi system adjacent to that negative charge to matter, it has to actually be able to connect to the anion. It has to be able to distribute. For example, if we look at benzoic acid, we see that its pKa is about 4.7, which is almost identical to that of acetic acid. Why is that the case? Well, even though we have this benzene ring here, which looks like we might be able to delocalize the negative charge just like with phenol, in reality what happens is that this negative charge can bump like this onto this oxygen, but it can no longer move into the benzene ring. We can't push this negative charge down here without making an excess of bonds onto this carbon. We would have to give that carbon 5 bonds, and that's impossible. So we cannot actually delocalize into this benzene ring, and so benzoic acid doesn't benefit from being adjacent to the benzene ring. It's just the same as a normal carboxylic acid. So I want to go ahead and home in here on phenols, which are a prototypical example of how electronically active withdrawing groups and resonance impacts the acidity of a given molecule. Specifically for a phenol, the position of the electron withdrawing group makes a very large difference. If we look at phenol, which has a pKa of 10, we can compare it to ortho-nitrophenol, which has a pKa of 7.2. Why is this molecule so much more acidic? Over 1,000 times more acidic, in fact? Well, it has to do with the fact that the nitro group can absorb through resonance the excess electron density from that O- and form a new resonance structure as shown on the right. And the way that would work is we would take this O- and we would push the bonds as such to get the negative charge onto this oxygen. And because we're sharing that negative charge to another electronegative element, another oxygen, that is going to make a very large difference, and we're going to have a significant increase in acidity, 1,000-fold in fact. Now, withdrawing substituents need to be at the ortho or para positions to make phenol more acidic, and the ortho and para positions are those shown, either those adjacent to the O- or those directly opposite the ring from the O-. The other two positions are known as meta positions, and they don't impact the acidity as much because they do not participate in resonance. And we can go ahead and look at that by looking at some differentially substituted nitrophenols. If we look at the ortho-nitrophenol on the left, we know that it has a pKa of 7.2. It's more acidic because that O- can go ahead and bump down into that oxygen very nicely. However, if we look at paranitrophenol, we once again see that it has a very similar acidity of 7.15 because this O- can once again bump all the way down into that oxygen very nicely, and we delocalize into the nitro group. However, we run into a problem at the meta position. Meta-nitrophenol is going to have a pKa of about 8.4, which is appreciably less, about 10-fold less acidic than the ortho or para. Why is that the case? Well, if we draw the resonance structure for the meta position, what we'll see is that the nitro group gets skipped over in the resonance chain. If we go ahead and take this negative charge and try to push it, we'll find that in order for this carbon here not to form 5 bonds, this bond has to move, and the negative charge ends up on this carbon. We skip over the nitro group, and so the electron density never makes it to that nice electron withdrawing oxygen, and so it is going to be appreciably less acidic than the O or P nitrophenols. And that is true of any electron withdrawing substituent at the meta position for a phenol. There are several other common withdrawing groups which I want to make you aware of, and those are going to include a carbonyl group attached to the O or P positions. We can go ahead and distribute the electron density nicely into that carbonyl group. We can also use a cyano group or a nitrile, which can do the exact same thing in addition to the typical benzene ring. So we add more resonance structures and put the negative charge nicely on that nitrogen or on this oxygen. We can do either. And we can even go ahead and add another phenol group, which will distribute the electron density nicely onto this whole other benzene ring, which will add negative charges to these 3 positions here. Not quite as good as a strongly electronegative atom, but will make the molecule appreciably more acidic as well. I also want to go ahead and look at the effects of resonance on some nitrogen and carbon acids, because oxygen isn't the only important source of acidic protons. If we go ahead and look at nitrogen, the first molecule we should consider is ammonia. Ammonia is very non-acidic. It has a pKa of about 38, which, in compared to water, we're talking 10 to the 25 times less acidic than water. However, if we change one small thing and we add a carbonyl group here, we change the acidity profile exponentially. We see now that it has a pKa of about 16. Why is that the case? Well, this nitrogen, if it were to lose a proton and gain a negative charge here, would look something like this structure shown on the right. And that negative charge can go ahead and delocalize, because it's adjacent to that double bonded oxygen, and give the following resonance structure. And now we have the minus shared between an O and an N. It is no longer localized, it is delocalized, and that makes the anion far more stable, specifically the fact that it's delocalized to an oxygen. And so we have a much, much more acidic proton. We've increased the acidity about 10 to the 20 times. Now, we can also go ahead and take it one step further and look at this molecule, succinimide, which is going to do the same thing. It's going to, if we had a negative charge here on this nitrogen, it can distribute it to either oxygen, right? So we can go ahead and put the partial negative on each of these oxygens, making it much more acidic, and that's going to give it a pKa of about 9.5, even a little bit less than our phenols, which is pretty interesting, right? On the other hand, we can look at some carbon acids. We know that methane, CH4, is going to be very non-acidic, even more so than ammonia, because carbon's less electronegative, and we find indeed the pKa is about 50. Super non-acidic, one of the least acidic molecules out there. However, just by adding a carbonyl group, and we make acetone, the pKa shoots down to about 20, which is 10 to the 30 more acidic. Now, why is that the case? Well, if we were to deprotonate one of those CH3s and give a negative charge on that carbon here, that can go ahead and delocalize. Let me draw the arrow a little better. Can delocalize into that oxygen to give us the following resonance structure, and this is known as the enolate ion. It's a particularly stable anion, which is very significant for organic reactions, and significantly changes the acidity profile of a carbon. You significantly increase the acidity of those protons on that CH group. Even more acidic if we add two carbonyls. If we have this 1,3 diketone species, we'll see that the pKa is about 9, even more acidic. And the reason is that this, if we were to take a negative, take out one of those protons there, this negative charge can go ahead and delocalize into either of those oxygens, which is going to give it a great deal of stability and make that molecule quite acidic. So I want to go ahead and close off by looking at the acidity of some more complex molecules which balance some inductive and resonance effects. And we're going to go ahead and rank them from 1 being the highest acidity and 5 being the lowest acidity. So our first set of 5 molecules are going to look as follows. And they're relatively complicated, so don't freak out. We're going to break them down piece by piece. So we want to know which is the most acidic proton in any of these molecules. To do that, our first step should be to think in terms of functional groups. What are the most acidic functional groups that we know of? Those are going to be carboxy acids. So we want to go ahead and scan and see, are there any carboxy acids present? And the answer is no, we don't see any carboxy acids in these molecules. So we want to go ahead and then move to our next most acidic group. That is typically going to be an OH. So do we have any OHs present in these molecules? And the answer is yes, we have quite a few. 4 of the molecules, the first, third, fourth, and fifth molecules all have an OH group. The next question is, okay, do we have any OH groups which, if deprotonated to form an anion, would be stabilized by resonance? More specifically, we want to think, are there any resonance stabilized anions that will delocalize to a strongly electronegative atom? And the answer is yes. We might think to look at these 2 molecules here. We see that we have an OH group next to a double bond, and those are next to 2 double bonded oxygens, which is nice. We see, however, that the first molecule is not the same as the second molecule. If the first molecule here on the left were to become an anion, it could in fact delocalize. The double bond could push as follows, and we could get the negative charge onto that oxygen. So this negative charge will be shared by 2 oxygens, and so it will be nicely stable. However, if we were to deprotonate the next molecule, the 4th molecule here on the list, it could not delocalize up into this oxygen. There is no double bond in this position to be able to bump. It could delocalize this into this carbon, but that's not very significant. 1 carbon doesn't contribute very much. So we know that out of these 2, the left one is going to be much more acidic because of the stability of the anion, and in fact it will be our most acidic molecule. What about this final structure on the right? We see we have 2 nitro groups and a benzene ring, which is quite promising. Well, we know that if this minus charge were to delocalize, we can delocalize it onto the ortho and para positions of the benzene ring. However, the nitro groups are left out. They are meta-nitro groups, which means they are not going to participate in resonance. They are, however, going to be nicely inductively withdrawing, And so the combination of the delocalization into the benzene ring, like a normal phenol, and the induction of the nitro group will make it pretty acidic. Not quite as acidic, though, as number 1, but it will be more acidic than the other molecule we looked at, the other square ring, because of the resonance effect. Whereas this one can only delocalize into the 1 carbon, this one can delocalize into 3 carbons. So these molecules will be 2 and 3 respectively, with the greater resonance leading to greater stability as compared to the single carbon resonance. Now, what about these two on the left? Well, we see that we have a nitrogen, which is going to be able to delocalize into a benzene ring, sort of like a phenol. This is called anion. And we have an OH group, which is not able to participate in resonance, but which has some nicely inductively withdrawing groups, and oxygen is more electronegative than nitrogen. So, which is going to be more acidic? Does the resonance matter more, or the inductive effects? In this case, it turns out this molecule is going to be more acidic. The OH proton is significantly more acidic than NH protons. And in fact, we know that we looked earlier at the molecule an amide, which is a nitrogen next to a double bonded oxygen, and we saw it has a pK of about 16, which is the same as an OH proton with no resonance or inductive effects. So this molecule, while it does have resonance, is nowhere near as nicely stabilizing as a double bonded oxygen, because carbon is not very good at carrying negative charges. So this benzene ring will stabilize the anion somewhat, but nowhere near enough. So the OH is still going to be much better at stabilizing the negative charge than the nitrogen, and so the molecule on the left is more acidic than the molecule on the right. And so we have the following ranking. We can then go ahead and look at the next set of 5 molecules. So once again, we scan through and we notice that this time we do have carboxy acids. In fact, we have 2 of them. We have this one here and this one here, which is going to be more acidic. Well, we have some resonance effects at play in the first molecule here, this one here, which aren't at play in the second molecule. We have these nitrogens, which can each delocalize their a lone pair of electrons into the ring. And some neat stuff will happen, right? So these nitrogens are going to push their electron density, and what we'll see is that they can actually push their electron density into that carbonyl group. They can push it into the carboxy acid group, which is going to give this oxygen a partial negative charge to begin with. That is actually going to make this OH group less acidic, because if it were to ionize, we're going to have a negative charge next to an already partially negative oxygen, which is going to have some sort of electrostatic repulsion, right? So we can see that these nitrogens pushing their electron density into the ring is actually going to make the carboxy acid group a little bit less acidic. So this is going to be number 1 and this is number 2, right? Now, what about the remaining 3 molecules? We have formaldehyde, acetone, and some sort of amide. Well, we know that the protons here on the acetone can delocalize into the oxygen. We saw that already. And the same will be true of the amide. That is not the case with formaldehyde. Formaldehyde, if it were to ionize, would put the negative charge on this carbon, which is not able to delocalize into that oxygen. It's just stuck on that carbon with the pi bond there. So we might think, oh, well, formaldehyde has no resonance effects. It won't be that acidic. But as always, organic chemistry has plenty of exceptions for us, and it turns out formaldehyde is number 3. Why is that the case? Well, it turns out that the strongly inductive withdrawing character of that oxygen makes it such that the negative charge is slightly better stabilized on that carbon than the other 2 molecules, and it turns out there's a special sort of resonance occurring between that hydrogen and the oxygen known as hyperconjugation, and we'll talk about that later on. But for now, let's just appreciate that there is always an exception to the rule. Resonance doesn't always win. Now, what is going to be next? Which is going to be more acidic, the acetone or the amide? Well, both are going to involve ionizing one of those protons off the carbon and delocalizing it into the oxygen. So which oxygen carries the negative charge better? Well, this nitrogen is also pushing its negative electron density, the lone pair, into that oxygen. And so that oxygen, just like our benzoic acid that we looked at, is going to start off with a partial negative charge, which is going to make it slightly repulsive to further ionizations. And so, as a result, this molecule on the left, the acetone, is going to be more acidic because its oxygen is going to be more receptive to another negative charge, whereas the molecule on the right is already dampened by that lone pair of the nitrogen, which is going to reduce the ability of the molecule to ionize further. And with that, we've actually reached the end of the content for this video. Thank you guys so much for watching, and if you enjoy what you saw, please like and subscribe to the channel. Make sure to check out the other videos in the chemistry playlist to learn more. And if you're looking to branch out, check out our other science playlists. See you next time!